Hello student, welcome to our lesson today, and in today's lesson we are going to look at applications of electromagnetic induction. We start with the first one, which is transformers. Now a transformer is defined as a device that transfers electrical energy from one circuit to another by mutual induction. It consists of a primary coil, and in this primary coil we have an AC input signal. And then it has secondary coil, and this secondary coil gives us what we call the output signal or output voltage. Now the coils are wood on a common soft iron. We are going to see the reason why we use soft iron. A transformer, we have seen that a transformer works on an AC current and not DC current, because an AC current changes in both magnitude and direction and therefore produces a changing magnetic field. Remember, when we were talking about the Faraday's law of electromagnetic induction, we found that an induced EMF is produced when we have a changing magnetic field. So the AC current is the one that is producing a changing magnetic field, and therefore it is able to give us what we are calling the induced EMF. That induced EMF is transferred to another circuit through mutual induction. When you use direct current, this one does not change in magnitude, it does not change in direction, and therefore it cannot produce a changing magnetic field. Now we have two types of transformer. One, we have step down transformer, and in this transformer it has the following. One, the primary turns are more than secondary turns. N is referring to the number of turns. So when we write NP, this one is referring to primary turns, and NS is referring to the secondary turns. So we are saying NP is greater than NS. Now number two, the primary voltage is greater than the secondary voltage. Remember, when you have the number of turns being more, each turn produces EMF, and therefore the more turns that you have, the more induced EMF that you will have. Therefore, when you have many turns in primary, it implies that we will have a higher voltage in primary than in secondary. In other words, we are saying the changing magnetic flux in the primary induces a relatively smaller secondary voltage than primary voltage, because in secondary coil we have fewer number of turns. Then another thing is that the current in primary coil is lower than the current in secondary coil. Note the symbols there. Then from there we have another term that we need to understand, the turns ratio. Now this one is defined as the number of turns in the secondary coil to the number of turns in the primary coil. Now when we come to the step down transformer, this ratio is less than 1. In other words, we are saying that the number of secondary divided by the number of primary turns, which is the same as the voltage in secondary divided by the voltage in primary, is less than 1, and this is what we call the turns ratio. Now in primary coil or in step down transformer, this ratio is less than 1. Now it has this as the symbol, or we can say that this is an indication or a diagram that is showing the step down transformer. Look at the number of turns here, the primary coil. They are many than the secondary turns here. Again, we are saying that these two are wood on a soft iron core. Then we have the electrical power source. Here is where we have the input, and here we have the output. So this is a common transformer, a step down transformer. The symbol for that is this one. As you can see, this one is representing many turns in primary. Then we have the iron core, then fewer turns in secondary. This is the symbol of a step down transformer. Then we come to step up transformer. Now in this one, the primary turns are less than the secondary turns. It is like the opposite of step down. In other words, we are saying NP is less than NS. The secondary voltage is greater than the primary voltage, and the current in the primary is higher than the current in secondary. So this is how it looks like. The number of turns in primary are less than the number of turns in secondary, and the symbol is like this. You can be able to see the symbol here. We have the fewer turns in primary and the many turns in secondary. Again, what you're supposed to note is that the turns ratio, where we have seen that it is the number of turns in secondary divided by the number of turns in primary, or the voltage in secondary divided by the voltage in primary, is greater than 1 in step-up transformer. Now we move to useful transformer equations. We have seen that the secondary voltage divided by the primary voltage is equals to the number of turns in secondary divided by the number of turns in primary, and this is what we have called the turns ratio. Now this one, or this formula, is what we call the turns rule. Mathematically, we can say that Vs, that is the voltage in secondary, divided by Vp, which is the voltage in primary, is equals to Ns, that is the number of turns in secondary, divided by Np, which is the number of turns in primary. This is mathematically representation of turns rule. The turns rule assumes that there is negligible resistance. So electrical power is equals to voltage times current. This one is learned in Form 3. So whenever we talk of power, we say that it is the rate of doing work. So when we talk of electrical power, we take the voltage times current. So it is P VI. So when we talk of power input, it will be the primary voltage times primary current. That is Vp multiplied by Ip. And the power output will be secondary voltage times secondary current. In other words, it will be Vs multiplied by Is. Note the input, we are talking of primary, and the output, we are talking of the secondary coil. Then from there, we have that the efficiency of a transformer. We define this as the ratio of power output to the power input, and this must be expressed as a percentage. In other words, efficiency will be power output divided by the power input multiplied by 100. But we have seen how to calculate the power output, where we are saying that the power output is Vs, that is the secondary voltage, multiplied by the secondary current. Then we have the power input, which is the primary, that is Vp multiplied by Ip. This should be Ip. Then you multiply by 100, it should be expressed as a percentage. Now this formula is used to get the efficiency of a transformer. When we talk of an ideal transformer, we assume that there is no energy lost, and therefore the efficiency of an ideal transformer will be 100%. And if that is the case, then it will be 100, which is our efficiency, will be equals to Vs multiplied by Is divided by Vp multiplied by Ip, then we multiply by 100. If that is the case, then it implies that if this 100 and 100 cancels out, then we can be able to get that Vp multiplied by Ip will be equals to Vs multiplied by Is. In other words, the power input will be equal to the power output, because there will be no energy lost in an ideal transformer. Now from this formula, we can make Ip the subject of the formula. If you look here, if we divide through by Vp, we will get that Ip is equals to Vs multiplied by Is divided by Vp. That will give us the primary current. So in other words, if you divide through by Is again, you will get that Ip divided by Is will be equals to Vs divided by Vp. And Vs divided by Vp is what we call the turns ratio, which is the same as Ns divided by Np. So in other words, you can be able to get the current if you have the number of turns, or you can get the voltage if you have the current. This is a useful formula in a transformer. We move to an example. A transformer with a primary coil of 400 turns and a secondary coil of 200 turns is connected to 240 volts AC mains. Calculate the secondary voltage. We proceed as follows. Vs over Vp is equals to Ns over Np. This is from the definition of turns ratio. We want to get the Vs. So Vs will be Ns multiplied by Vp divided by Np, and then you substitute the values that are given. You will find that the voltage Vs is equals to 120 volts. Then from there we move to another example. A transformer is to be used to provide power of 24 volts ceiling bulb from an AC supply of 240 volts. Find the number of turns in secondary coil if the primary coil has 1000 turns. Again, we proceed as follows. Using this formula for the turns ratio, we substitute our values. Our Vs is 24, our Vp is 240, Ns is what we are looking for, and Np is 1000. So we make Ns the subject by multiplying through by 1000, and after that, and simplifying, you will get that you get 100 turns. That will be the number of turns in the secondary coil. Then we move to energy losses in a transformer. We have four main causes of energy losses in a transformer. One, we have the flux linkage, and in this one is when all the magnetic flux produced by the primary is not linked with the secondary coil. Therefore, we have a reduction of EMF in the secondary coil because not all magnetic fields are linking with the secondary coil. That is what we call the flux linkage, and that is a source of energy loss. Now, this one can be reduced by using efficient design of transformers to ensure there is maximum flux linkage. Then from there we have that the secondary coil is wood over the primary coil, and the coils are wood next to each other on a common core as shown in figure B, like this one. This is now the designs that will ensure that all the magnetic flux in primary are linked to the secondary. Therefore, there will be no flux linkage. So we can either use the first one where we are saying that the secondary is wood over the primary, or number two, we have that they are wood next to each other. So it means that the magnetic flux in primary will be linked, all of them will be linked to the secondary coil, and therefore there will be no flux linkage. Then another way of reducing or power losses is the resistance of the coil, what we call the copper losses. And this one can be prevented by using a thick copper wire, and this will reduce the heating effect. Then we have number three, the eddy currents in the coil. Eddy currents are associated fluxes that tend to oppose the flux change in the primary. In other words, we are saying that you have other currents that are moving within the coil or within the copper wire. So that way they produce other currents. Instead of now having the current that is moving to the secondary coil, we have other eddy currents that are produced within the copper wire. That way, this can be reduced, or this reduces the power transfer to the secondary. And we are saying that eddy current can be reduced if the core is laminated. And this is laminated using thin sheets of insulated soft iron plates. And this will cause minimal heating effect. Then we have hysteresis loss, and this is where now the energy losses or energy is lost in form of heat. Remember, when we are talking of a magnetic or a transformer, we are talking of primary coil that is wood on a soft iron. So what is happening is that there is magnetization because there is formation of what we call electromagnet, because we have a soft iron and we have coils, and there is current that is passing. So we will have magnetization and demagnetization. Now the energy is lost in form of heat in this process of magnetizing and demagnetizing the soft iron core. Remember, we are using AC, and when we are using AC, there is change in direction and change in magnitude. So every time the current reverses, there is demagnetization, and when it changes, then there is magnetization. So there is these two processes that are occurring or that are changing within seconds. That is magnetizing and demagnetizing. And in the process, you find that there is heating effect, and that heating effect makes now the power to be lost or energy to be lost. And that is what we call now hysteresis loss. And this can be minimized by using a core of soft magnetic material, because soft magnetic material can be magnetized and demagnetized easily. Then we have a practical transformer. A transformer that we use in a practical way is the one that is used in power stations along transmission lines, and this one generates a lot of heat. Now, to avoid or to help in cooling, we have what we call a cooling oil, and this is an oil that does not evaporate easily. Now, small transformers are cooled by use of air, but a well-designed transformer can have efficiency of up to 99%. However, the presence of air reduces its efficiency. Remember, we have talked of ideal transformer, where we have said that ideal transformer has an efficiency of 100%. But now we are saying we have a practical transformer that we use in power stations. Now this one, to ensure that there is cooling, we use oil that does not evaporate easily. But we still have other small transformers that can be cooled using air. Then from there we have the assignment. This is just testing what we have just learned. So make sure that you revise well, you prepare, and then come and attempt the assignment. So thank you, and let us meet in our next lesson.